Hi, I'm Aditya NG and I will be presenting our work on D³Nav. The traditional AV stack involves having a lot of sensors and models for each of the perception and planning tasks. In practice, this is both fragile and difficult to scale with raw data. An interesting thought experiment to run is to ask yourself, would you be able to drive if you were given a VR headset that showed you only the inputs that the AV 1.0 stack feeds on? More often than not, driving with this data becomes challenging since a lot of important visual cues and context are dropped. AV 2.0 gives us many advantages including computational homogeneity, scalability, and generalizability with data. To build a data-driven driving agent and an end-to-end simulator for autonomy, we built D³Nav. We set out to answer the question, how do you build a robust world model? We take inspiration from LLMs. LLMs are pre-trained on large-scale text data with the task of predicting the next word, and then are fine-tuned on a task like chat or classification. The idea is that the next token prediction task provides excellent supervision for building a robust world model given sufficient data. With a similar intuition, we pre-train our driving model on the task of predicting the next video frame. We then fine-tune the model to produce a driving signal as well. First, we set up our model for pre-training. We use the VQVA to condense data down to a compact embedding space for our GPT. Here are a few results from our pre-training stage. We observe that our encoder is able to correctly encode and decode frames, and our world model is able to predict the next frames. After the pre-training stage, we set up our model for fine-tuning. For this, we attach a trajectory quantizer to feed in and extract the trajectory tokens from our model. We also build a simple model predictive controller to compute the steering, throttle, and brake values. Here are a few results from the fine-tuning stage. We observe that our trajectory quantizer can correctly encode and decode trajectories, and our world model is able to predict the next trajectory token along with the next video tokens. Here is a demo of our model deciding the control signal on a video from our dataset. The 3D point cloud is generated by another model to get a sense of scale. Finally, here are a few metrics. In conclusion, we build quantizers to efficiently compress high-dimensional video and trajectory data into embeddings. Our world model can predict future video frames and the desired control signal. Our training pipeline uses minimal human labeling throughout the entire process. This progress is particularly beneficial for building a driving agent or simulating training scenarios where real-world data is scarce or incomplete. Thank you for your time.